Hi everyone. Now I'm going to explain factorial design, which is a design of experiment and which is a part of quality by design. So here the example which is taken is a nanolipid formulation in which after conducting few experiments, it was observed that drug is to lipid ratio and temperature are the main factors that are influencing vesicle size, that is response. So here the example which is shown is 2 square with 4 midpoints, that is totally 8 runs. So further from the half normal and normal plot, so select the highest factor, start selecting from the highest range A and B. And from the Pareto chart, it can be observed that the values which are above the T value that are important and need to be considered. In this case, both A and B are above the T value limit, and hence it can be considered that they are important for the experimentation. And further from the ANOVA, it can be observed that the model is showing value less than 0.05, which indicates significance of the terms. And even the curvature is less than 0.05, that is indicating significance. If the curvature is not significant, it can be removed. So this curvature is an important term which plays an important role in the experimentation. So here this, if the curvature is significant, further you can augment this particular factorial design to that is can be extended to response surface designs also. And further from the statistics, it can be observed R square value is closer to 1, that is 0.9970, and adjusted R square and predicted R square values, they are less than 0.2, which indicates that model is fitting the data and can reliably use to interpolate them. And even adequate precision is greater than 4, which can be said that it can be used to navigate the design space. CV will be considered in few cases. The value should be as low as possible. And further from the coefficients, you can observe factor A is showing a positive effect and factor B is showing negative effect on vesicle size. That is nothing but increase in the ratios of factor A increases vesicle size, and increase in the temperature decreases the vesicle size. So here, since increasing in the factor A, increasing vesicle size, but we need vesicle size to be reduced. So we need to reduce the factor A. And the other one, increase in the temperature is decreasing vesicle size. So hence, highest temperature can be selected to get lowest vesicle size. And from the diagnostics, it can be observed that first one, normal plot of residuals, which follows a normal straight line distribution, and generally look for sometimes the S-shaped curves, which indicates transformation may provide better results. Residual versus predicted, residual versus run, residual versus factor. So this indicates there are random scattering, which indicates significance of that particular model. And box class plot, which indicates transformation is not required. And further from the predicted versus actual values, so once you place this cursor onto the points, you can observe from the left bottom that predicted values and actual values are very closer to 1, which indicates that predicted are very much closer to actual values. And Cook's distance indicates the point should not be closer to the outlier. And the next one is leverage plot, and even this should not be closer to 1. And if it is closer to 1, it can be reduced by replicating the points. And same thing can be observed in the report, that is Cook's distance, leverage, and other plots. And further, for studying the design space, you need to select the criteria. So as from the coefficient estimates and analysis of the design, we have observed that the factor 1 should be minimized, and you can also give the preference, that is importance to the which is assigned to the goal. And temperature, it was observed, need to be maximized, and obviously the vesicle size need to be minimized. Look for the solutions. So three solutions were observed. So this is design space. Further, from the graphical representation, even we can observe the perturbation plots. So whenever the factor shows steep slope or curved lines, that also indicates significance of the particular factors in the experimentation. And further, this is a contour plot which is used to navigate the design space. So first of all, as I said, it is a part of QBD. So in the risk assessment, you have to further set the goals and criteria, that is starting from quality target product profile and critical quality attributes. And especially in the quality target product profile, we need to set what is the vesicle size that need to be uh, required and that need to be observed for your formulation. So since we have fixed here less than 500, that may be it may start from 100 to 500. So that's why the space it is showing 300, 400, 500, and the prediction is showing 193.3. Further, you can also add contours. So since as low vesicle size is required, so you can observe. So here by placing the point on 253.066 vesicle size nanometer, you can see the x1 need to be kept at 1.25, that is 1 is to 1.25, and temperature need to be maintained at 59.5. And further, 300, in order to get 300 vesicle size, 1 is to 1.4, and the x2, that is temperature, which can be kept at 55.1. So like this, you can add the contours and you can observe what is the space which is required. Establishing design space is very much required, especially during FDA submissions and also during scale up post approval changes, because this will help really, which will reduces the rejections during approvals. Further, it can also be extended to graphical also if required for studying the overlay plots. Thank you.